12, 13, 14, 15, 16, 17, 18. There's 19 of you in here right now. And I said, how many ways could I arrange you in a line? What would you do?
18 times 17 times 16 times
19 times 18
yeah.
times 17, all the way down to what?
That just seems like an awful lot.
It does, doesn't it? Okay, you want to know how much that is?
How much is it?
Okay, well in your calculator, if we want to go ahead and multiply a lot of numbers all the way down to 1, I don't know if I even have this in my calculator, but you guys in your calculator should be able to hit a button that says, see this little exclamation point right here? It's called a factorial button right there. Okay? And in your calculators, if you hit 19 and then your probability button, do you have like an exclamation point as an option there? Okay, hit that. 19 and then exclamation point like this. That means that there are, oh my gosh.
Whoa. And I still I got 1.2 ones.
Wowzers. Hundreds.
I got the X with the exclamation.
Do I know how many different ways I can arrange you guys?
121 trillion.
Mine is with an E to the 17. 1, 2, 3.
This would be 121 quadrillion, 645 billion, 100 million, 408,000,
Why don't I have 1.2?
or 408 million. That's a ton. 19 times 8. That's getting pretty big, isn't it?
Yeah.
Is there any way I could arrange you guys in one day?
Yeah.
Do all 19 ways in one day?
No.
No.
Well,
There's
yeah,
no way.
really do. Not in 2 days.
Okay.
Let's ask
Think about winning the lottery. Nope. How many different ways could I arrange you? Wouldn't happen. Okay. So we're going to start talking about things like that. How do you arrange things? How many different ways are there to arrange things? Okay. And this is going to be all part of what's titled Permutations and Combinations. Michael, you want to read that for me, essential question?
How can a tree diagram help you visualize the number of ways in which two or more events can occur?
Okay. So how can a tree diagram help you understand that? All right, we'll talk about what that looks like. But here's the deal today, kids. In order to answer that question, we need to use a formula for the number of what? What's this word right here? Permutations, and we're going to use a formula for the number of what?
Combinations.
Okay. Let's make sure we understand the difference between the two. So first of all, in our vocabulary, a permutation. A permutation is an arrangement of what?
Objects.
In which order is?
Important.
When I say important, or I say order is important, it says you might have the same 3 things, like we had the same 3 boys up front, but every time I put them in a different order, that was a different arrangement. Okay? So order is going to matter. And the way we write this, you're going to see it written as N, the number of things that we're talking about, arranged R different ways. Okay? All right? Then, n factorial. You're going to hear me talk factorial a lot here. Factorial means this. It means for any positive integer n, the product of the integers from 1 to n is called n factorial and is written as n times n minus 1 times n minus 2 all the way down to 1. So for instance, if I want 4 factorial, this means 4 times 3 times 2 times 1. So in your calculator, I want to make sure you can do a factorial in your calculator. Punch in 4 exclamation point and see what you end up with.
Why isn't advanced math
24 is what you should get, so it takes some time. 4.
Yeah, it's 24 out.
So 4 times 3 times 2 times 1 is what that is. 4 factorial is going to equal what, kids?
24.
24. Okay? Then we're also going to talk about combinations. Here's the deal. 19 people in here, right?
Yeah.
Okay. I'm going to choose a basketball team right now. All right? I might choose 1, 2, 3, 4, and 5 right here. So I might choose Adam, Michael, Jacob, Josh, and Allie as my basketball team. Now, that's a team. There's 5 of them there, right? And I chose them in a certain order, but what if I chose Josh first, Allie second, Adam third, him fourth, and Jacob fifth?
I'm almost trash.
Hey, my question is this. Did the order change in the way I chose them?
Yes.
Yes, but it's still the same team?
Yes.
It's still the same team, okay? So sometimes we're going to talk about combinations, meaning, hey, this is what I chose out of the whole group. I chose them in a different order this time, but it's still the same what? Group. It's kind of like saying this, kids. If I roll a die twice, and I say, I want to get a 4 and I want to get a 6. What are my ways I can get a 4 and a 6? Well, I can get a 4 on the first roll and a 6 on the second roll, but isn't that the same as getting a 6 on the first roll and a 4 on the second roll? You want to get a 4 and a what? 6, okay? When we start talking about combinations, order doesn't matter. It doesn't matter how you get to that final group. So you're going to hear me talk a lot about the difference between permutations and combinations, all right? Combinations you're going to see written as N, capital C, and an R, and I'll talk about what that means, all right? And then finally, kids, fundamental counting principle. The fundamental counting principle, also called the counting rule, is a way to figure out the number of outcomes in a probability problem. It says basically you do what? Multiply the events together to get the total number of outcomes. We've talked about that already, okay? So let's get into this right here. Let's start talking permutations. The thing I think that's really important about the definitions, permutations, order is what? Order is important, okay? So what I say is this. In a permutation, 1, 2, 3 is different than 3, 2, 1. Those would actually count as how many different sets? 2. They are not the same. They count as 2 different sets. 1, 2, 3 would be different than 3, 2, 1. That would be an example of permutation. How do you arrange things? Okay, that's 2 arrangements. But in a combination, I would say that these here are not the same. But in a combination, if I have, I don't know, values 1, or card 1, card 2, and card 3, that's the same as having card 3, card 1, and card 2. Okay? This means they are the same. So would I count that as 1 combination or 2 combinations?
1.
Just 1. Okay? So under the condition of combinations, whatever the order is, it doesn't matter, because you still have the same 3 things. But when we're talking permutations, the way in which you arrange things, the order in which you arrange them is going to matter. It counts differently, okay? So permutations, think what word here, kids? They are different arrangements. Combination, they don't care about the arrangement. They just want to know, is that group the same or is it different? Okay? Can you remember that?
Yes.
Example 1, titled Talking About What, kiddos? Counting permutations. It says, consider the permutations of letters in the word what? Pencils. A P, an E, an N, a C, an I, an L, and an S. Okay, how many letters are in there?
That's 7. Yeah, but then you have to take some letters out. Yeah.
Are all the letters the same? Is there any overlap?
No.
They're all different, aren't they?
Yeah.
So it says, in how many ways can you arrange letters? When we talk about arrangements, that's saying we want to know how to arrange all the letters. Now, this one right here is talking about all, how many letters up here, kids? 7 letters. Okay. So what we would do here, kids, is this. My first letter, how many choices do you have to choose from? 7. Now, once that first one's taken, how many letters do you have to choose from for the second one? How about the third one? And down to what? And kids, if I go all the way down to 1, this is the same as saying 7 times 6 times 5 times 4 times 3 times 2 times 1. Somebody punch that in. 42 times 5 is 210. 210 times 4 is 840. How much?
5,040.
5,040 ways I can arrange those letters. Now, do this for me, kids. In your calculators, type 7 factorial and tell me what you get.
Same thing.
5,040, right? 5,040. Okay. That's just 7 factorial. 5,040 ways. All right. Now, how is the second example different than the first example?
Less numbers.
There's less letters. You're still choosing from the same 7 letters, right? It says, in how many ways can you arrange how many of the letters this time, kids? So how many letters are you going to have?
It'd be 3 times 2 times.
Be very careful. These letters are all in the bag. So that first one, we're only going to have it 3 letters long. So how many possibilities could go in here, kids? From all of these up here. Not 6, but 7 first, right? There's 7 different letters that could take this first place. Then down here, 6. And then what? Why don't I go down to 4, 3, 2, 1?
Because you only got 3 letters.
There's only 3 letters. I've exhausted that. So this is like saying, ooh, we're not going to use all 7 letters. We're only going to use 3 of the 7 letters. How many words or how many 3-letter combinations or permutations or arrangements, I guess I should say, how many 3-letter arrangements can you come up with? Well, 7 times 6 times 5, how many do you get?
The enter button.
210 ways. Okay. Now, that's the way to count them. First of all, when we think about that way, do you understand what we're doing right there?
Yeah.
Why did I go 7 times 6 all the way down to 1 in the first one?
Because they wanted that 7 letter.
Yep. Excuse me, I have deja vu going on right
That's
now.
okay. Adam gets it home.
Anybody ever have that experience?
Yeah, it's kind of weird, you know?
Okay.
I had it yesterday.
Some I don't like.
You want to know what's going to happen in my deja vu that I have going on right now?
What?
I'm going to get a text from somebody that says we came into some money. I hope that's true. If you don't see me tomorrow, you know what happened.
There was something creepy in my backyard at my area.
All right. Why did I only go 7, 6, 5 here, kids?
Oh, I remember my dream yesterday now.
How much?
It was here.
Say again, Bree, so I can hear you. It's only 3 letters, okay? You had 7 to choose from on the first one, 6 on the second one, 5 to choose from on the third. We don't go any further, okay? Don't go any further because we don't need to. All right, so let's talk. Second page here, kids. Core concept. What's the word up there, kids? Permutations, okay? It says the number of permutations of n objects given by the following. N, P, N equals what, kids? N factorial. Here's the deal. We talk permutations when we talk about how are you going to arrange your letters. Because when you arrange stuff, a different arrangement is a different type of set. So if you think of it this way, in that first example, kids, how many letters did you have to choose from? How many letters were you using? And what did we get for an answer? Okay. So the way we read that is this. If I'm talking about arranging stuff, we would read this as a permutation of 7 things, 7 at a time. Okay? They said that's equal to n factorial. Well, we knew that. But another way to punch this into your calculator, kids, is this. Go to your calculator. Okay? I want you to hit 7 first. Okay, hit 7 first, and then you guys with the probability buttons hit the NPR button. 7 NPR, and then hit 7. What's that kicking out for you? 5,040. That's saying you're taking 7 letters and we're going to arrange them using how many of the letters, kids? 7. And what do you get for an answer there? 5,040. Now, another one right here. The number of permutations of n objects taken what? R at a time, where R is less than what? N is given by the following formula. N is going to be, this is read as N, it's a permutation of n things, R at a time. And its formula is n factorial over n minus r factorial. But I'm going to help you with the calculator here, kids. Basically, in that second example that we looked at, how many letters do we have to choose from? Had 7 to choose from, of which you were only going to use what? 3. So what I would do is say, how do I arrange that? Well, you'd say that that's a permutation, because we're talking arrangements of 7 letters, but we're only using what? 3 at a time. Punch that in your calculator. We know it better equal what value?
210.
Does it equal 210?
Sure does.
Okay. So anytime you're talking about how to arrange things, if order matters, what is this called? Not a combination, buddy. So here's my example to you, kids. Here's my example to you. There's 19 kids in here.
Yes.
I'm going to choose an arrangement of 5 of you. I want to know how many different ways I can choose 5 of you. So you're going to go permutation of 19 things.
19P5.
Yep. How many ways can I arrange 5 of you from this class?
1,395,360.
1,395,360. So if I had to say today, I'm going to arrange 5 of you,
Just 5 out of those ones.
any 5 of you, and I'm going to do all the arrangements. How many arrangements would I have to make? There's 1 million. What's the number again?
1,395,360.
There's 1,395,360 ways I can arrange you for position 1, 2, 3, 4, and 5 up here out of you 19 kids.
Wow.
That's a lot, isn't it? Okay. So who says that small classes can't make big numbers? Ginormous. Yes, sir.
Wait, no.
Oh, you were just answering the question. All right. Let's use this.
Question, buddy.
Sorry.
Michael, let's get you back on track. Would you read example 2 where it says using a permutation formula?
8 people serve on a committee. In how many different ways can a chairperson, a recorder, and a treasurer be chosen from the committee members?
Okay, so how can I choose? 1, 2, 3. First person I choose is the chairperson. Second person I choose is the recorder. Third person I choose is the treasurer. How many ways can I choose those positions? 8 what? Where's the 8 coming from?
The number
The 8 people.
The 8 people that I want to arrange. And of the 8, we're only going to arrange how many?
4.
How many?
4.
A chairperson, a recorder, and a what?
3
Oh,
out of.
oh
my
my
God! You did not.
Holy cow. I thought I was wrong for a second.
Stop looking at me.
What do you guys get when you do that?
330.
336 ways. So if there's 8 people sitting there. Now guys, why is this a permutation? Why does order matter? Because the first person chosen would be a what? Chairperson. So and that's very different than being in the second position, who is a recorder. Why does order matter there? Because there's different titles to those people. Now if I was making just a team of 3, that's going to be a very different example. Because you'd be on the same team. But these are different roles within that group. And that's why permutation matters there. Okay? So what was the value again here? Okay. Moving on. Moving on.
You mean ways?
Is that what I said? What's the problem up there?
You have it at.
No.
Like that? Ooh.
Hey, Alex.
Because we're all Charger Chromebooks out.
All right.
I'm just gonna leave my phone.
Let's talk. Finding a probability using what, kids?
Permutations.
All right.
Yeah.
Dre and Brian are auditioning for a part in a school play. Anyway, Dr. Dre.
They're probably rapping.
There are 15 people auditioning. And the order of their auditions is chosen at random. Find the probability that Dre auditions last and Brian auditions what?
Well,
Second to last.
Well, there's only one way that can happen, right?
Yeah.
Yeah.
Just that Dre's better than Brian.
So
Save the best for last.
they have to be the last 2. And there's only one way that can happen. All right, they have to be that position, and the other one has to be the other position. You guys agree with that?
Yes.
You guys agree with that?
Yes.
Yeah.
So second to last and last. So it's only one way that can happen. But how many different ways can they arrange this, kids?
A lot.
A lot.
Because Dre.
How many people are there?
Dre.
15.
15.
Oh.
So there's 15 different people, kids. How am I going to figure out how many different arrangements there would be to go in order for that?
15p something.
15p, all what? Are we just going for a few of them, or are we going for all these kids?
All of them.
All of them. So it'd be 15
15.
factorial, right?
Oh yeah.
Right?
Yeah.
So it's just 15p.
15p, 15, or just 15p?
Which is the same
15p,
thing.
15.
It's a big number, isn't it?
15p.
I bet so.
It's huge.
Now, think of it this way, though. No matter what, the last two positions have to be what and what? Dre and who?
Brian.
You guys agree with that?
Yes, sir.
No matter what, that has to be that way. But down here you said there's 15 factorial ways to arrange that, right? Agree with that?
Yes.
Now, where Dre and Brian are already at right there, kids, do you see that?
Yes, sir.
Dre and Brian are going to be the last two chosen. Does that mean there's only going to be one order before them, or could there be multiple orders before them?
Multiple, because they got like the 15.
How many other kids are we talking about besides Dre and Brian in this?
13 other kids.
Okay, so 13 other kids. So I got to arrange those 13 other kids in front of Dre and Brian how many different ways?
I don't know, whatever 13 factorial is.
13
Factorial.
factorial. So the probability that Dre and Brian would be the second to last and the last one would be, well, we can arrange this up here 13 factorial ways because this has to happen right here, right? The other 13 I can put in any order or before that, can't I? And then that's out of a possible how many total arrangements, kids? 15 factorial. So in your calculators, do this. Let's go 13 factorial.
Wow. Huge.
Factorial, that's going to be a big number, but we're going to divide it by what, kids?
It's like 5.
15 factorial, because we're looking for a probability, right? Where's my factorial button?
That's not that big.
What percent of a chance is it that they're the last two? If I move the decimal 2 to the right. 0.4, is it okay if I call it about 0.48%? So this is equal to 0.0048, which is approximately what percent, kids? Yeah, so it's less than 1%, isn't it?
My God.
I have a question here, kids. I'll go back to things that we talked about that were mutually exclusive. Just think about this one person that's at the very end. Who's at the very end? Brian? No, I've got the order mixed up. These should be mixed the other way. This should be B and this should be what? Doesn't really matter. You guys get the idea. This should be a D right here. But kids, think about it. What's the probability that this kid is in this spot for sure?
0.48%.
Isn't there a 1 in 15 chance he falls here? And then once he falls here, this person falls here, there's a 1 in 14. Somebody take 14 times 15 for me. 210, good. Somebody take 1 and divide it by 210. Let's see what that equals.
0.0476 48.
Isn't it the same thing?
Yes.
Haven't we kind of talked about a problem like this already?
Yes.
Okay, makes sense to you?
Not really, but
What do you mean, what really?
I'm just kind of confused.
How many
how it
orders can there
works.
be? What's the probability you get in that spot?
No,
There's
see,
a
I
1.
get that. I get how you got it, but like I don't get like.
But I understand this forecasting.
What do you mean, why?
I mean, like.
Well, there's 13 different ways I can arrange
No,
these
I
people,
get
right?
that. Like I
Okay.
get it, but like just don't.
And once they get
why
it's actually way
like
easier
that.
now.
It just is.
I don't know.
Okay, all right, let's talk here, kids. You guys are going to help me. Counting what now? This is very different. It says count the possible combinations of what, kids?
6 letters.
How many letters are here?
6.
And it says count the possible combinations of, 4 letters. What I'm going to tell you is this, guys. The following happens here. P, Q, R, S, and T is the same as Q, R, S, P. Oh, why did I do that?
We don't know why.
I was only choosing 4, right? These are the same exact thing right here because they contain exactly the same what letter?
Numbers.
Same exact letters, okay? We start talking about combinations. The way you arrange them doesn't matter. You start talking about groups. Is the group the same, all right? So counting combinations means that how many of the same group can you make, okay? I want you guys to see how many groups of 4 you can make. Take a minute and do that. Conveniently, I left you how many boxes?
3, 6, 9, 12, 15, 18, something like that. 15.
I could have P, Q, R, and S, couldn't I?
Yeah, but it's 15.
SQR.
Couldn't I have P, Q, R, and T? You guys agree with that? Could I have P, Q, R, and U? Could I have P, R, S, T?
I don't know, King.
Can I have P, R, S, U?
SU.
What? Guys, you're 7, 8,
Can I have P, S, T, U? How about Q, R, S, T? How about Q, R, S, U? How about Q,
How about PSU?
S, T, U?
Penn State University.
And -1. How about R, S, T, U, kids?
You're so mean.
Get this from you.
I drink.
Okay, give me something I'm missing.
T.
Do I have P,
Gotta
Q,
get some
T,
T's
U
in
up there?
bud.
T.
P, Q, T, U would be one.
What about start one?
R, S, Q, what? P, R, S, Q? I have that already, P, Q, R, S.
But
I already have that grouped.
T.
Do I have P, Q, S, T?
Do you have Rust?
Do I have P, Q, S, T? I don't see P, Q, S, T, do you?
No.
Do I have Rust up there? Yeah, R, S, T, U. How about P, Q, S, U? You guys see P, Q, S, U up there at all?
No.
Okay, now I don't know what the last 2 are, but I'm just going to tell you there's 15 different ways up here. All right? Now, again, understand this order, P, Q, R, S, is the same as what? Okay, it's the same group. We're saying how many ways can you group 4 letters together? We don't care about the order of them. We just want to know, is the group exactly the same or not? Okay, and I'll come back and get those other 2. But guys, this leads me into the next core concept here. Next core concept is not about permutations, it's about what? Combinations. And it says the number of combinations of n objects taken r at a time, where r is less than n, is given by the following. This is read as the number of combinations, n things r at a time, is n factorial over n minus r factorial times what? Okay. Okay, so right here, as an example, it says the number of combinations of what, kids?
4 objects.
Number of 4 objects taken at 2 at a time. So if I had 4 kids to choose from to make a team of 2, and we were going to play 2 on 2, if I was the coach of one team, how many different combinations of kids could I choose? So in your calculator, 4c2. Or if you want to do this, kids, you can do this as 4 factorial up top for n. What's 4 minus 2, kids, going to be? For the n minus r part, 2 factorial times, what's r again? Well, 2 factorial. What's 4 times 3 times 2 times 1 up top? What's 2 times 2 in the bottom? So if I had 4 kids and I was going to choose my team,
It would be 6.
how many possible teams could I put together? 6 of them. Does the order in which I chose them matter? No, because if Allie and Audrey were my team, it wouldn't matter if I chose Allie first and Audrey second or vice versa. It would still be the same team, right? Does arrangement matter in combinations?
No.
No.
So, we go back to that example right here on the previous page. How many letters are we talking about in that alphabet? Okay, so we're arranging, or we're not arranging, we want to know how many combinations of 6 letters can I form groups of 4 with. Somebody run that in their calculator.
15.
15.
It's almost like that.
There's 15 ways. Permutations, does order matter?
Yes.
Yes, because it's the way you arrange it. Combinations, does order matter?
No.
Because it doesn't matter how you arrange it. So let's take a look at this last example right here. The art teacher has selected how many projects, kids?
13.
13, including one of yours and one of your friends, to use in a display case in the hallway. So Brianna and Tristan, your art projects are in the hallway out of 13 kids. Okay? Does it matter which order they were chosen?
No.
No, the only thing that matters is those 2 pictures are the ones that are hanging in the art gallery. It says the projects are placed at random. There is room for 2 projects in the middle row of the case. What is the probability that your project and your friend's project are the 2 placed in the middle row? Well, the first thing is this. How many drawings or projects do they have to choose from?
13.
Okay, now,
There's
no matter what, they're going to choose how many of those projects?
2.
Does it matter in which order they choose those 2?
No.
Makes no difference because those are the 2 that are going where?
In the middle.
So let's figure out how many possible ways they can choose projects. What's combination 13 things 2 at a time equal? It's going to be a big number. $13.
Huh?
78.
78?
Yes.
This is 78?
Yeah.
So how many combinations of 2 can they pick?
78.
Well, kids, how many combinations of Brianna's and Tristan's projects work? Well, there's 78 possible ways. I could take Tyson's and I could take Josh's, or I could take Jacob's and I could take Josh's. That's just one. Okay? How many different ways can I take theirs? There's only one way that those are the 2 chosen, right? There's only one way that those are the 2 chosen. Doesn't matter which order they're chosen, but there's only one way that it gets there. So the probability that happens then is 1 out of what? 78. Okay? Why 1 out of 78?
Because that's the only one that would have the certain.
I remember doing that all the time.
What's the 78 represent?
They know combinations.
Number of combinations. The number of way I can choose 2 projects out of a total how many?
13.
Only one of the 78 is.
And there's only one of the 78 combinations that's Brianna and...
T.
That's so
Okay.
Are we doing number 5?
Are we going over 5?
No, we're not.
13.
Yes, we are. Did I skip it?
Yeah.
What?
No.
Well, what?
You for Example 5, you skipped.
Oh, I'm sorry. I am so sorry.
You almost broke my little heart.
43? That's 9 minutes.
Michael, would it mend your heart a little bit if I let you read example 5?
Oh, yeah.
Go for it.
You are listening to music. You have time to hear only 3 songs from your playlist of 16 songs. How many combinations of 3 songs are possible?
So how are you going to write this, kids?
16 C3.
Okay, it said combinations, so it doesn't matter which order you hear them as long as you hear all 3 songs, right?
Yes.
So it says 16 songs. How many different ways can you hear 3 of those songs? How many?
560.
560 ways, okay? Guys, the key concept here is, do you understand when arrangement matters and when arrangement doesn't matter?
Yes.
Arrangement matters for
The people.
permutations. And arrangement, or order, if you will, does not matter for what? Combinations. Okay. So I'm going to go